Hello there and welcome back to the Science Sleepy Minds. Tonight you're drifting somewhere between consciousness and cosmic weirdness. So let's do what any self-respecting sleep traveler would do. We're building a light clock. That's right. Picture yourself standing in the middle of a quiet spacecraft. Not a flashy one, just sleek and silver, floating out past the moon. In your hands, a little device that looks like two mirrors facing each other, a beam of light bouncing perfectly up and down between them. Tick-tock-tick, simple, right? But then your ship starts to move, fast. And suddenly, that beam of light isn't just going up and down anymore, it's zigzagging. From your perspective, it's still bouncing the same way. But to someone watching from outside the ship, the light has to travel farther, diagonally now, and since light can't speed up, it just takes longer to complete each tick. You just invented time dilation. Congratulations, you're now aging slower than your friends back home. You probably won't survive this being the overwhelming realization that the faster you go, the weirder time gets. But hey, it's good for your complexion. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And tell me, where are you watching from, and what time is it in your corner of space-time? Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You rest your hand on the light clock. It's not ticking slower because it's tired. It's obeying the fundamental speed limit of the universe. Light always travels at the same speed in a vacuum, 299,792,458 meters per second. And because it won't budge on that number, everything else, space, time, your sense of how long until dinner, has to adjust instead. It's hard to feel time stretching. You don't get a little notification that says, you've just lost 0.000003 seconds. But when you're moving fast, really fast, like aboard a ship nearing the speed of light, those tiny adjustments build up. 100th of a second here, a second there, an entire year, maybe, if you're willing to cross the galaxy and come back home to find everyone mysteriously older than you. In 1905, Albert Einstein published his theory of special relativity and turned the idea of absolute time into a quaint little antique. Historians still argue whether Einstein came up with the light clock thought experiment himself, or if it was later used just to make the math more palatable. Either way, the principle it shows is real. The faster you move, the slower time ticks for you. But only from someone else's point of view. From your own perspective, nothing feels different. You're still stuck in this ship trying to reheat a bag of freeze-dried mac and cheese, and wondering if the toilet will ever stop making that weird chirping noise. But to someone watching from Earth, you're living in slow motion. Let's get tactile for a second. Imagine you're skating on a perfect sheet of black ice in a spacesuit, holding your light clock. The beam inside ticks every second like a heartbeat. You start skating faster and faster. From your point of view, everything's normal. You're just skating. But someone watching from above sees the light beam inside your clock traveling in a diagonal path now, because you're moving sideways as it bounces up and down. That diagonal path is longer, but since light speed is fixed, the only way it can keep up with reality is by slowing down the ticks. That's time dilation. And no, this isn't some sci-fi exaggeration. GPS satellites have to correct for this effect every day. Their atomic clocks tick just a bit differently in orbit, because they're moving faster than we are, and also higher in Earth's gravity, but we'll get to gravity warping time in another section. If engineers didn't account for that discrepancy, your GPS would think you're about 10 kilometers from where you actually are, which might explain why it tried to send you into a lake that one time. Fun side note, there's a weird little tale that ancient Egyptians may have used sunlight to time their rituals, essentially creating very primitive light clocks using obelisks and temple architecture. While historians still argue whether this qualifies as intentional timekeeping or just a happy alignment of sun and shadow, it's oddly poetic. Thousands of years before satellites and spaceships, people were already bending their daily rhythms around beams of light. Back in your ship, you feel the engines rumble as your velocity increases. There's no jolt, just a gentle hum under your feet. The stars outside stretch a bit. Not really, but your brain says they do, and who are you to argue? Your clock's beam zigzags faster and faster, stretching each second like taffy. You check your watch. Still ticking, still ordinary, but someone back on Earth would swear your heart's barely beating. That's the funny thing about special relativity. It's only special because it assumes you're in inertial motion. No acceleration, no gravity. just coasting at a steady speed. And even then, time becomes this slippery, stretchy thing that refuses to behave. A second isn't always a second anymore. It's a suggestion. As the ship coasts faster, you begin to wonder, what would happen if you kept accelerating? Could you slow time down so much that the rest of the universe just zips past you? Could you leave Earth for a year and come back to find 1,000 years have passed? Short answer, yes. Long answer, pack snacks. Time dilation isn't just a theory. It's been confirmed again and again in particle accelerators, where particles called muons, we'll meet them soon, live longer the faster they go. It's been confirmed by clocks flown around the Earth on airplanes. Heck, even you, right now, sitting or lying motionless on your bed, your head is aging infinitesimally faster than your feet because it's a teensy bit farther from Earth's centre of gravity. Physics is petty like that. But for now, you're just you, drifting through space, your light clock clicking away its lopsided rhythm. Tick, tock, slow, tock. You blink. The soft blue glow of your ship's control panel reflects in the curved glass of the window, stars stretching like tiny frozen sparks. Outside, the void hums its ancient silence, and in this strange cradle of motion, your mind drifts into the dreams of a man who also spent a lot of time thinking while staring into nothing. Einstein. The name floats up like a thought bubble in your drowsy brain. Not the wild-haired caricature holding his tongue out, though yes, that one too, but the 26-year-old patent clerk in Bern, 1905, sitting at his desk, quietly reshaping the universe between paperwork. The year would later be called his Annus Mirabilis, Miracle Year. 4 papers. One of them, the special theory of relativity. No lab, no funding, no telescope, just trains, clocks, and imagination. You curl up in your zero-gravity hammock and drift closer into one of Einstein's thought experiments, the ones that redefined our understanding of time. Imagine you're sitting on a beam of light, riding it like a cosmic surfboard. This was one of the first ideas young Albert wrestled with. What would you see? Would the light beam just hang there in front of you, frozen? That didn't make sense, because no matter how fast you move, the speed of light always stays the same. It's the universal speed limit. Everything else, space, time, mass, contorts and cooperates to preserve it. Like the universe agreed to one rule and decided to twist itself into knots to avoid breaking it. So if you can't ever catch up to light, that means things start getting weird the faster you go. Time, especially. You're still in the beam of a light daydream, watching the scenery blur as you pick up speed. And here's the kicker. This isn't even sci-fi speculation. Historians still argue whether Einstein derived his theory from hard math first or from these dreamy visualizations, but one thing's certain. His gift wasn't just logic, it was visualization. Back to that imaginary train. Let's say you're standing on the roof of a train moving near light speed and you strike a match. To you, the flame flickers normally, but to someone on the ground watching the train scream past, the match strikes in slow motion. Why? Because from their perspective, your time is running slower, and this isn't about bad eyesight or optical illusions, it's fundamental. It's how the universe maintains consistency in light speed. You roll onto your side, eyes still open, drifting through a different version of that train. This time, you're inside the carriage. A lightning bolt hits both the front and back of the train at the same instant. To someone standing on the embankment, it's clear. They see both flashes at once, but to you, sitting inside the speeding train, the flash from the front seems to reach you after the one from the rear. Because you're moving forward. Same event, different order. Now your brain's humming, trying to sort it out. You want to label the flashes simultaneous, but that label has become slippery. What's at the same time depends on who's watching and how fast they're moving. Simultaneity isn't. Not always. This is the heart of special relativity. Events don't just happen now, they happen in context. Time itself is relative, woven together with space into something called space-time, which behaves like a stretchy, flexible grid. And you're the sleepy astronaut tangled in its threads, like a cat batting at a laser pointer on a quilted cosmic couch. A little fringe fact for you. In the early 20th century, right as Einstein's theories were starting to stir the academic pot, a few spiritualist circles grabbed hold of relativity to claim time dilation proved the existence of the afterlife. See, they argued, if time can stretch infinitely, maybe death isn't an end, It's just a really slow passage to somewhere else. Historians still argue whether these movements genuinely believed in the physics or just liked the poetic edge. Either way, relativity has always had a flair for the mystical. Back aboard your ship, you pull up a simulation. The screen flickers to a cartoon of two astronauts, one at rest, one moving fast. Their watches drift out of sync. It's the famous relativity of simultaneity at work. But seeing it play out in real time is unsettling. 1 second to you might be 5 seconds to someone else. Which one is true? That's the trick. There's no universal now anymore. There's just now for you, in your own frame of reference. Einstein didn't love the word relativity, by the way. He preferred the term invariance, because while time and space stretch and twist, the underlying laws stay the same for everyone, everywhere. It's not chaos. It's consistency through transformation. But theory of invariance doesn't exactly roll off the tongue. You tap the screen and watch the fast astronauts circle a planet. As they loop around and return to their friend, their clocks are no longer aligned. One has aged more, and not because time felt different, because time was different. Each tick of the fast astronaut's heart was farther apart from the perspective of the one left behind. And that's the hard truth. You don't just feel like time is slower on fast ships, it is slower. You could take two identical twins, send one on a round trip near light speed, and when they return they'd be biologically younger. Of course, getting a twin to volunteer for that experiment might be a whole other challenge. Your own ship isn't quite that fast yet, but you imagine what it would be like. A short nap for you, weeks or months back on Earth. Your plant's overgrown, your cat furious, everyone speaking slang you don't understand, a few trending dances you'll never be able to replicate. The idea tugs at something deeper, doesn't it? That time isn't some neutral stage you move across. It's part of the motion itself, stretchable, personal, and easily bent by speed. A gentle beat brings you back, your light clock still ticking quietly in the corner. You smile. It's a weird comfort, knowing that your moments are yours alone, running on their own schedule. Out the window, the stars haven't moved, but you have. And slowly, tick by slower tick, you begin to leave the world you once knew behind. You press your forehead gently against the cool glass of the observation window. Outside, the stars are motionless points of light, but your ship is hurtling forward, slipping faster and faster into deep space. It's quiet in here, almost too quiet. So you entertain yourself the only way someone stuck in relativistic motion knows how, by chasing beams of light. That's not just poetic nonsense, that's exactly what Einstein did. Again. Because clearly the man had no intention of ever getting any sleep either. Picture it. You're sprinting through empty space with all the desperation of someone who forgot their coffee on the roof of a speeding car. You're chasing after a beam of light, and you're getting close. So close. But no matter how fast you run, the beam keeps pulling away. You speed up, it still outruns you. You go even faster, and yet the distance remains stubbornly the same. That's because, as the universe has quite rudely dictated, the speed of light is a universal constant. You can't catch it. You can't even gain on it. It's like trying to beat a treadmill by running on it faster. It'll just speed up with you. This idea, deceptively simple, flipped physics on its head. In classical Newtonian mechanics, speeds add. If you're running at 5 miles per hour on a 50 miles per hour train, your total speed is 55 miles per hour. Simple, logical. But try applying that to light and suddenly math stops being your friend. Let's say your spaceship is flying at 90% the speed of light. You turn on a flashlight and shine it forward. Your gut says the beam should be moving at 190% the speed of light relative to someone behind you, right? Nope. Still just light speed. Always light speed. This is where your ship's clocks, along with your very definition of time, start to unravel. Because in order for light to remain constant for every observer, even the ones in motion, the universe has to start adjusting things. Space compresses, time dilates, measurements warp. Your sense of now goes out the window, if it was ever really in here to begin with. Historians still argue whether Einstein ever fully accepted how strange his own theory was. He never quite liked the idea of time being purely relative. It just offended his tidy sense of order. But physics didn't care about his feelings. It cared about consistency. And to keep light speed the same, time itself had to become slippery. Let's break it down with something simple. You're inside your ship again, sitting with a nice warm cup of rehydrated mystery tea. You shine a flashlight across the room. The beam hits the wall in a fraction of a second. Easy. Now imagine someone outside the ship watching you zoom by. From their perspective, the beam of light doesn't just travel across the room, it also moves forward in space because your ship is moving. So it travels a diagonal path longer than what you observe inside. But here's the trick. The outside observer still measures that light moving at the same speed, which means the only way for that longer path to happen without breaking the speed limit is if your time is slowed down from their perspective. The same journey takes longer. Your second is just longer. It's like the universe fudging the stopwatch just to keep the beam's speed intact, and you don't even notice. That's the spooky part. From your own viewpoint, nothing's changed. You can still sip your tea, scratch your nose, complain about how the toilet still chirps. But everyone else, stationary observers, earthlings, maybe even some space lizards you pass by, they all see you aging more slowly. Imagine the paperwork nightmare. Here's a fun, nerdy fringe fact. In the mid-20th century, some sci-fi authors proposed fictional tachyons, hypothetical particles that always move faster than light. According to theory, if they exist, spoiler, we have zero evidence, they'd experience time in reverse, as in, cause would follow effect. You fire a tachyon gun, and the wall explodes before you pull the trigger. That's probably not happening in your current ship unless your coffee maker is hiding something. Still, chasing light always leads to bizarre consequences, because the closer you get to it, the more space contracts and time stretches. If you could somehow reach light speed, a big if, your time would freeze completely from the perspective of the outside universe. You'd be frozen in your moment, immortal in motion, yet unable to move forward in your own time. At that point, the dream of faster travel becomes more philosophical than practical. You think about this as the stars outside start to warp. Not really bend, not yet, but your brain knows something's off. Your ship's speed increases incrementally, and suddenly you're aware of how the universe is cooperating, bending its own rules to keep the lights on, so to speak. Here's another twist. If your ship had windows that could perfectly display relativistic effects, no filters, no adjustments, you wouldn't recognize the stars at all. You'd see them compressed into a glowing point ahead of you, a phenomenon known as relativistic aberration. The entire night sky would distort. Behind you, darkness. Ahead of you, everything. It's a bit like looking down the throat of time, and right now you're accelerating. Not dangerously, just steadily. Engines humming. You can feel it. Not in your body because inertial dampeners or whatever, just in your clock, in your light, in the growing disconnect between your shipboard seconds and Earth's relentless judgmental calendar. You wonder briefly if anyone back home is watching your position. Maybe someone staring at a monitor watching a blip crawl across the stars, unaware that for you just a few hours have passed. For them, maybe a few days already. Back in 1971, the Haffel-Keating experiment flew 4 atomic clocks around the world in commercial airplanes. When they reunited those clocks, they were no longer synchronized, just as predicted. Time dilation had left a fingerprint, minuscule but real. Now scale that up, but if time stretches at airline speeds, what happens to you in this star-surfing spaceship? Well, you might nap for an hour and wake up to find your favourite band broke up, got back together, and released an ironic country album. You might send a birthday message that arrives too late to matter. You might return to find someone you loved. Aged. That's the price of chasing light. But there's beauty in that too. You're not just watching the universe. You're moving through it in a way no one else can. You've unhooked yourself from the standard timeline. Your seconds are sovereign. And though it feels strange, wrong even, to think that time is bending just to keep your flashlight normal, it's strangely comforting to know the universe has a plan, even if it's wildly inconvenient. Outside, the stars stretch into streaks. Your tea is cold. And somewhere back on Earth, someone is already older than they were when you last blinked. You're floating now, not just in the literal sense of being aboard a high-velocity spaceship with artificial gravity politely turned off, but in that dreamy, slightly unanchored state of mind that comes from thinking way too hard about clocks. Your ship hums quietly. The observation screen cycles through distant galaxies. You're curled up, sipping on some thick space cocoa, and trying to remember how birthdays even work anymore. Because tonight, we're talking about twins. And not the fun matching outfits kind. No, we're talking about the relativity kind. The kind that break reality just by being born on the same day. Picture it. 2 identical twins, born minutes apart. Same height, same genes, same suspicious cowlick. Let's call them Alex and Sam. They grow up together, prank each other, and at some point, because this is a thought experiment, one of them gets offered a ride on a spaceship that can travel at near light speed. Sam stays home, Alex takes the ship. It's meant to be a short mission, just a few years at most from Alex's perspective. But by the time the ship loops back around to Earth and Alex steps off, Sam is a decade older. Wrinkles, grey hair, probably a story about how texting just isn't the same anymore. Alex, though, looks like they left last Tuesday. This is the twin paradox, and it isn't actually a paradox, just a very inconvenient truth of physics. Time really does pass more slowly for the travelling twin, and not just a feels like slow, this is hard, measurable biological aging. So what happened? It all comes down to motion, and more specifically acceleration. Remember, in Einstein's special relativity, if two people are moving at constant velocity relative to each other, they can each argue that the other one is experiencing time dilation. It's a symmetric situation. But the moment one of them turns around, hits the brakes, reverses direction, comes home, something shifts. That acceleration breaks the symmetry. The travelling twin changes frames of reference, and when they return to compare clocks, they find they've lived less time. So poor Sam has had to explain memes to 3 whole new generations while Alex just blinked. Historians still argue whether this thought experiment was first proposed by Einstein himself or by Paul Langevin, a French physicist who elaborated on it in 1911. Either way, it's been haunting physics students ever since, and it's been confirmed. Not with full-grown astronauts yet, but with particles, atoms, and those hyper-accurate atomic clocks that never sleep. And yes, this would absolutely apply to you. If you, a perfectly ordinary human, took a round-trip journey at near-light speed and came back, you'd be younger than everyone you left behind. It's not a trick. It's not some glitch in the Matrix. It's just how time works when you play with speed. A quirky little historical footnote. In the 1930s, Soviet science fiction writers got very into this concept. There was even a short story where a cosmonaut returns home after a brief mission to find Moscow replaced by mossy ruins. Society collapsed, and Earth speaking a whole new language. So yes, the Russians were doing time dilation apocalypse drama before it was cool. Back in your ship you wonder about Sam, or rather, your version of Sam, your friends, your family, your old barista who knew exactly how much oat milk to add without judgment. If you were to return, would they recognise you? Would you even recognise them? Time dilation makes space travel lonely. Not during the voyage. No, that part is peaceful, weirdly serene. It's the coming back that breaks you. Let's say you leave Earth at 99.5% the speed of light. You travel for what feels like 5 years, turn around and come back. You've aged 10 years. But Earth, it's age 100. Everyone you knew is gone. Cities are different. Fashion is confusing again. And someone has definitely invented a new social media app called Schroedergram. Because the universe insists on treating time like a flexible suggestion, instead of a reliable companion. You grab your tablet and do a little math. Not much, don't worry. Just enough to make your tea go cold. The formula for time dilation in special relativity is based on the Lorentz factor. It tells you just how much time stretches at a given velocity. The closer you get to light speed, the more extreme the effect becomes. At 0.9 c, 90% light speed, a minute for you is about 2.29 minutes on Earth. At 0.99 cents, one of your minutes stretches into over 7 minutes back home. At 0.999 cents, one of your minutes equals 22 Earth minutes, and at 0.999999 c, well, your spaceship might as well be a time machine. We're not quite there yet. Our fastest spacecraft, like the Parker Solar Probe, reach speeds of around 0.0002 c. Impressive, yes, but nowhere near relativistic enough to make your birthdays awkward. Still, astronauts do experience time dilation. Tiny amounts, but measurable. Gennady Padalka, the most space-seasoned human in history, spent over 878 days in orbit. Thanks to time dilation, he's technically 0.02 seconds younger than if he'd spent that time on Earth. Not enough for a party, but enough for bragging rights. You float toward the rear window of your ship and look back. Not that you can actually see Earth from here, but the metaphor is nice. It's strange to think that even at this very moment, someone on Earth is technically aging faster than you. Feet on the ground, spinning gently with the planet, They're in a different frame of reference, a slightly accelerated one. There's a softness to that thought, like a quiet ripple in the cosmic pond. You are moving, therefore your time is your own. Your every second, stretched and shifted, becomes a personal timeline. The laws of physics demand it. They bend around your motion like warm taffy, slow and stubborn, and there's no escape clause. Your twin, your Sam, would welcome you back with tears in their eyes and too many candles on the cake. Maybe they waited, maybe they didn't. Either way, their time moved faster, their journey was shorter, and yours? Well, you took the long way through the shortest route. So when someone tells you time flies, smile politely, and remember that on fast ships time doesn't fly at all. It lingers, it takes its time, and maybe, just maybe, it waits for no one, except you. You shift in your sleep capsule cocoon, the faint glow of the ship's internal systems washing the room in that familiar soft blue. There's a low hum, like a cat purring somewhere in the walls. It's not a warning, it's just the engines gently inching you closer to something terrifyingly simple, the speed of light. You're not there yet, but you're getting close, and the closer you get, the weirder time becomes. Imagine time as taffy. Delicious, stretchy, sticky taffy. At slow speeds, it stays pretty firm, bite-sized, normal. But as you approach light speed, slouching towards C, as the poets would say, that time taffy stretches, elongates, resists your every attempt to bite down on a single clean second. That C, by the way, is the symbol for the speed of light in a vacuum. It's not just a fast number, it's the fastest number, about 299,792,458 meters per second. The universal hard limit, a cosmic speed cap. And the closer your ship's velocity comes to that limit, the more dramatic time dilation becomes. At 10% the speed of light, the effect is basically negligible. At 50%, still not very spicy, but by the time you're edging toward 90%, 99%, 99.99%, oh, things get real stretchy real fast. You glance at your wristwatch. It still ticks normally. It's smug, unaware of the lies it tells, because out there, outside your ship, someone else is watching your time crawl like molasses poured uphill. And here's the cosmic irony. To you, everything inside the ship seems normal. You can brew your tea, check your inbox, wonder why the onboard AI insists on recommending 1970s disco playlists. But to an observer at rest, say on Earth, you look like you're moving through a dream. Slow, suspended, a ghost trapped between seconds. This isn't science fiction. It's the backbone of special relativity, a law written not in ink, but in the very geometry of space-time. And yes, there's math for this. The Lorentz factor, again, whispering its truths. Gamma equals 1 divided by the square root of 1 minus v squared over c squared. The closer your velocity v gets to c, the larger that denominator gets, and the more pronounced your time dilation becomes. Gamma starts near 1 and creeps upward like a snooze alarm with an agenda. At 0.99 cents, gamma is over 7. At 0.99999 cents, it's over 70. And at 0.999999c, gamma hits triple digits, and your ship might as well be an eternal cruise through the frozen river of time. Historians still argue whether Einstein himself ever imagined such close approaches to light speed as physically feasible, or just mathematically interesting. But modern physicists take it seriously, because even if we never reach C, we can always creep closer, and time will always obey. You stretch, floating a little in your capsule, and start to imagine what life would feel like near 99.999% the speed of light. Well, first of all, you wouldn't feel anything particularly strange. Your tea would still steep in 3 minutes. You'd still yawn after 2 episodes of that show you keep pretending to finish. Your shipboard time is self-contained. Your seconds, your minutes tick on like always. But outside your ship, decades, centuries, whole eras pass while you butter your space toast. In theory, you could leave Earth, travel for a subjective 5 years, and return to find the year is now 3,500. Humans might have evolved into polite jellyfish, or finally given up on social media. Either way, you'd be the ultimate tourist. Back on Earth, this all sounds pretty wild, but we've seen it in action. Remember those muons we'll be cuddling with in a later section? They're born high in the atmosphere when cosmic rays collide with particles up there. Muons decay fast after just microseconds. But because they're travelling near light speed, time dilates for them. From their perspective, they decay quickly. But from our perspective, they survive long enough to reach Earth's surface. They live longer, not because they've magically become more stable, but because they're racing toward us at speeds that stretch their lifespans. So even nature, messy, chaotic, radioactive nature, is obeying this slow-down rule. But let's play with this further. Let's say your ship could go just a hair under the speed of light, so close that the Lorentz factor was something like 10,000. That means for every second you experience, 10,000 seconds pass for someone not moving. That's nearly 3 hours for every heartbeat. And let's say you fly for just 1 week, ship time. Multiply that by 10,000, and you've got roughly 192 Earth years slipping by, while you sip on cold, rehydrated lasagna. You could time hop through history just by going fast enough. No wormholes, no flux capacitors, just velocity. Of course, there's a catch. There's always a catch. The closer you get to light speed, the harder it is to keep accelerating. Your ship gets heavier, not in the my luggage is over the weight limit sense, but in the relativistic sense. Your mass increases, your energy needs skyrocket. To reach exactly the speed of light, you'd need infinite energy, which unfortunately is not included in your standard interstellar fuel package. And even if you could do it, time for you would stop entirely. You'd become a frozen snapshot, an eternal passenger, stuck in a ship that could never age, never experience, never return. Light itself experiences no time. A photon is born and dies at the same instant, from its point of view at least. That's the cruel poetry of C. It is the speed at which time ceases to exist. A fringe philosophical tidbit for you. Some physicists and philosophers have speculated that maybe photons don't experience anything at all, that from their perspective, they are outside of time entirely, which raises some wonderfully absurd questions like, do photons remember things? Spoiler, no. You glance back at your watch, still ticking, but now you know it's lying, not maliciously, just relativistically. You can't blame it. It's doing its best in a universe where time bends like wet spaghetti. So you float back toward the cockpit, adjust the trajectory slightly, and watch the stars streak just a little more. You're not even at 0.9 C yet, but the weirdness has already begun to seep in. Messages from Earth take longer to arrive. Your onboard systems have to correct for Doppler shifts and time sinks. The music you're streaming from that old Earth server sounds just a little lower pitched. Okay, fine. You downloaded it. But still, and somewhere, far behind you, Earth spins on. Your friends age normally. Your houseplants have probably given up. The world slowly forgets you, not out of cruelty, but because your clock is no longer in sync with theirs. You've joined a slower timeline. 1 second at a time, you slouch toward the speed of light. And in doing so, you stretch the very fabric of time behind you. Your ship creaks, just slightly. Not in any worrying way. More like a subconscious stretch. Like the hull is sighing into its speed, settling into the laws of the universe it no longer politely obeys. Out the window, stars still shimmer like they've been glued onto a black velvet sheet. But the distances between them feel wrong now, subtly compressed. You close your eyes and let the motion cradle you, rocking back and forth on the waves of relativity. Tonight's dose of existential bedtime science, satellites and weird watches, and the tiny time tricks that already run your daily life, quietly governed by time dilation, whether you're zooming through space or just trying to find a coffee shop that's not 3 blocks behind your GPS dot. Let's come back to Earth for a minute, literally. You probably used GPS today, maybe not consciously. Maybe your phone auto-corrected your location to find tacos or told you that your Uber was arriving now, even though it was clearly stuck at that one cursed red light. What you didn't notice is that behind all of this digital wizardry is a delicate ballet of satellites, about 20,000 kilometers above your head, circling Earth at over 14,000 kilometers per hour. Each one is equipped with a ridiculously precise atomic clock, and those clocks tick wrong. Not broken wrong, relativity wrong. See, 2 effects are at war up there. First, the satellites are moving fast. Fast enough that special relativity kicks in and says, hold up. Time should be running slower for you than it does on the surface, which it does. Only by about 7 microseconds per day, but that's enough to matter. Now enter general relativity, Einstein's bigger, heavier hitting sequel. It says, wait a second, you're farther from Earth's gravity, which means time should actually be running faster. And that's true too, by about 45 microseconds per day. So the net result? Time on those satellites runs faster than ours, by about 38 microseconds per day. Tiny, right? Laughably small. And yet, if we didn't account for that offset, if the engineers behind GPS had just shrugged and said meh, your location would drift by about 10 kilometers a day. That's enough to throw off your morning commute, ruin drone deliveries, and confuse any self-driving car into gently parking itself in a hedge. It's not just theory, it's infrastructure. Historians still argue whether Einstein imagined that relativity would one day be used to help people find their nearest gas station. But GPS is perhaps the most casual, real-world application of his wildest insights. A system billions of people use daily, and it only works because scientists remembered that clocks in orbit tick differently than clocks on Earth. That's the magic of relativity. It's subtle until it isn't. Until it's telling your phone that you're actually not at the grocery store. You're 10 blocks away in someone's backyard. But let's look at the satellites again. Floating high above Earth, they're trapped in a weird contradiction. They're moving fast enough that time slows for them due to velocity, but they're far enough from Earth that time speeds up for them due to gravity. The result is that the clocks on board gain time compared to those on the ground. And those clocks are accurate to within a billionth of a second. That's like timing a race across the United States to within the width of a human hair. And even that precision still has to be adjusted daily to account for this wonky warping of time. Now imagine if we launched one of these satellites at a much higher speed, closer to, say, 90% the speed of light. Time dilation would become profound. One day for us could be weeks for the satellite, or vice versa, depending on how it moves. You might have heard the joke, time flies like an arrow, fruit flies like a banana. Well, in relativity, time flies differently depending on how fast you're flying. And sometimes it kind of loops around and asks if you're sure about your arrival time. Here's a fringe fact to chew on as you doze. There's a tiny but fascinating theoretical idea called gravitational time dilation farming. The idea is that in far future civilizations, you could set up colonies near massive bodies, like neutron stars, to stretch time for experiments or long-term data collection. One day there could equal decades elsewhere. Some fringe theorists even suggest storing information or consciousness there to pause it from the rest of the universe. Historians still argue whether these speculations count as science, or really clever procrastination. Back in your ship, though, you're not orbiting anything. You're just steadily increasing your velocity, inching your way closer to that absurdly unreachable speed of light. But even now, your onboard clocks are beginning to deviate from the timestamps you receive from Earth. You try to check your messages. The lag is noticeable. A ping takes longer than expected, and not just because of distance. It's because the data packets are now swimming upstream against a current of warped time. Your own computer system has to correct for your ship's dilation rate, translating messages from Earth's frame into your own before you can even read them. And if you didn't correct for it, let's just say your emails would get very confusing. Dinner's ready could mean last week or next month. This time drift isn't hypothetical. In 2010, the International Space Station had to account for about 0.007 seconds of time dilation during each 6-month mission. Doesn't sound like much, but even microseconds matter when you're syncing data, aligning orbits, or making sure two spacecraft don't high-five at 7,000 meters per second. You float closer to your wall panel, where a pair of synchronized clocks tick side by side. One shows Earth time, the other, your ship's internal time. They've started to disagree. You frown, mildly insulted by the betrayal. But it was inevitable. You're moving fast enough now that the seconds are no longer universal. They've become tribal, dependent on where you are, how fast you're going, and what kind of gravity you're dancing with. And if the clocks disagree, what else does? You start wondering if your age has diverged too. If someone on Earth could look at your birth certificate and say, "You're 36, but your body, your organs, your experience would all say, actually, I'm more like 35.998. Congratulations, you've officially joined the list of beings who age differently depending on their commute. And if that feels odd, remember that everybody experiences tiny amounts of time dilation all the time. Even you, sitting still on Earth, aging slightly slower at sea level than someone on a mountain. Not much, nanoseconds, but still, enough for physics to notice. So the next time you miss a deadline, just whisper, "Sorry, time moves differently for me." Technically, you're not wrong. Your ship rumbles again, a soft, lazy stretch. You glance once more at the clocks, shrug and float away. Whatever time they say, it's only true from here. You settle back into the captain's chair, not because there's anything to command right now, but because it happens to recline nicely and faces a screen that's currently running an old black and white simulation of a train. Yes, a train. Don't worry, this is exactly the right kind of sleepy science weirdness. You're about to time travel, on rails. The year is 1905. You're sitting on a very elegant, very European train with polished brass fixtures and a cup of something too strong for this early in the morning. Next to you sits a man with a massive moustache and the distant look of someone who's just invented a new way to break reality. This is young Einstein, before the fame, before the hair became its own creature, and long before his theories started rewriting GPS manuals. He looks out the window and squints, probably not at the scenery, but at the concept of time itself. Because this isn't just any train ride, it's the train ride, the one that gave Einstein one of his most famous thought experiments, and in this simulation, you're along for the ride. Let's play it out. Imagine this. You're on the train, moving smoothly along the tracks at a constant speed. Somewhere nearby, on the station platform, a lightning bolt strikes the front and back of the train at the same time. 2 flashes of light, one at either end. If you're standing on the platform watching the train go by, you see both flashes occur simultaneously. They reach your eyes at the same time, no problem. But if you're on the train and moving forward, you'll see the flash at the front of the train after the one at the back. Why? Because you're moving toward the location where the rear flash happened, and away from the location where the front flash happened. Light travels at the same speed in all directions, remember? So if you're in motion, your perspective of when the flashes arrive changes. To you, it looks like they happened at different times. Einstein used this to challenge the concept of simultaneity, the idea that 2 events can occur at the same time from all perspectives. Turns out they can't. What's simultaneous to one observer isn't necessarily simultaneous to another. Historians still argue whether Einstein rode an actual train while pondering this, or if it was a completely mental journey. Either way, this little scenario shattered the notion of absolute time. There's no universal now. There's only now from where I'm standing. You adjust your viewing angle as the simulation shows 2 beams of light racing inward toward the centre of the train. On the platform, they arrive together. Inside the train? Not quite. Even more unsettling. Both perspectives are valid. There's no privileged frame of reference. The person on the platform and the person on the train are both correct, just according to their own frame. Cue the existential crisis. This is why the train example is so powerful. It's not about trains, it's about how motion changes your relationship with time and space. If the order of events can change depending on where you're standing and how fast you're moving, then what is time, really? You pause the simulation. The still frame shows Einstein halfway through sipping his coffee, eyes fixed on something miles away, or possibly in another dimension. You've felt this before, not on a train necessarily, but in that surreal sensation of moving quickly past a landscape and watching it blur. Motion stretches things, it warps your perception, and it turns out, it warps the very fabric of the universe. You run your finger over the edge of your control panel, is warm, slightly vibrating like it's alive. You wonder what this same panel would feel like if you were watching it from the outside, moving past it at near light speed. It wouldn't feel the same. It wouldn't be the same. Space and time don't just bend at high speeds, they conspire. Let's revisit a lesser-known tidbit while we're time travelling. Back in the early 20th century, a few fringe inventors tried to build relativity machines that could demonstrate these ideas physically using rotating disks and bouncing lights. One even proposed using mirrors on a circular track to recreate the light clock effect. Historians still argue whether these machines were serious science or just the steampunk equivalent of vibes. Back in your ship, you toggle the simulation to show an Earth-based platform, stationary. A new animation plays. Now it's not lightning, but someone firing a laser at the front and rear ends of a moving spaceship. Same effect. From the Earth viewer's frame, both beams strike their targets simultaneously. But inside the ship, the light headed forward seems delayed, while the one going backward arrives early. This isn't perception, it's physics, because the light travels equal distances at the same speed, but you, the observer, are in motion relative to that light. It's unsettling, and kind of beautiful. This is why time dilation exists at all, because the universe is deeply committed to keeping the speed of light constant no matter who's watching. To do that, it has to adjust other things, distances, durations, even cause and effect if you push hard enough. Let's say you built a version of that lightning and train experiment in space, a spaceship with mirrors on both ends firing synchronized light pulses as you zipped past. You'd see the same pattern, simultaneity breaking down, one light pulse reaching you sooner, one later. And yet, the person watching from a stationary point, they'd still swear the lights fired at the same time, and they'd be just as right as you are. That's the wild part of relativity. It doesn't invalidate anyone's experience. It validates all of them, even when they completely contradict each other. Time has no single ruler. It's local, personal, selfish, like your ship's bathroom schedule. You float back from the screen, letting the old train dissolve back into digital vapor. The lesson has been learned, at least until you fall asleep and forget half of it. Simultaneity is broken. Trains have betrayed us. Light travels the same for everyone, and as a result, reality gets fuzzy at the edges. But you're okay with that. You're used to fuzziness now. You're coasting through a universe where clocks disagree, trains teach philosophy, and simultaneity is a quaint myth we once believed in. Your ship hums again. No lightning outside, just stars. Just time, quietly refusing to cooperate. You think of the old train one last time, barreling forward, dragging its own version of now behind it, and you smile. Because you're on a much faster ride. You roll over slowly in your sleep pod, half awake, half floating. The lights are dim, the hum of the engines has taken on a rhythmic lulling tone, and your thoughts are heavy. But not bad heavy, just full. Your ship is now deep into its cruise mode, gliding through the fabric of space-time like a hot spoon through honey. The readout on the wall says you've hit 0.85 C. Not quite brushing the edge of light speed, but enough to make time feel squishier. If clocks could sweat, yours would be dripping. And that brings us to tonight's dreamy dilemma, your very compressed day. See, you're not just feeling like time is moving differently, you're living it. Every minute you spend inside this ship hurtling through the cosmos is slowly peeling away from the timeline of the universe outside. From your perspective, totally normal day. You woke up, brewed a pouch of space-grade oolong, and spent 20 minutes trying to chase a rogue protein bar that slipped into zero gravity. But from someone watching back on Earth, those moments are longer, stretched. Their clocks are racing ahead of yours like over-caffeinated sprinters in a marathon you didn't even sign up for. Let's run the numbers. You've been flying for what feels like 24 hours, but Earth? It's felt closer to 30. That's 6 hours of reality that you'll never quite get back, because you never actually had them. They happened in someone else's frame. And if that makes you feel like your day is being compressed, you're exactly right. The technical term is time dilation, but when you're living it, it feels more like time is shrinking. Not in your body, not in your heartbeat or breathing, just relative to the rest of the universe. You're slipping into a tighter weave of time's fabric, where each thread takes longer to loop around the loom. You're not just moving through space, you're digging a tunnel through time, and the tunnel's narrower for you than it is for everyone else. Remember the light clock from way back in section 1? You've essentially turned your entire body into one. Your heartbeat, your thoughts, your breathing, all of it is ticking slower from the perspective of the outside universe. But to you, it's just another Tuesday. Now let's make this visceral. You're cooking dinner, well, reheating something suspicious in a packet that claims to be spicy mac with essential fibers. You pop it into the microwave equivalent built into your ship's wall. It runs for 2 minutes. You wait, smell the plastic warming, check your messages, maybe stretch your legs. 2 minutes pass. Meanwhile, Earth turns. People get in their cars, complain about traffic, forget what they came into the room for. And somewhere a small child is born, cries, eats a banana for the first time. Maybe not all in 2 minutes, but close. Because while you're making dinner, the clocks on Earth are moving just a little faster. They're running longer minutes. Your days are getting smaller and smaller, like compression artifacts in a file too large for the cosmos to download. This is what your life looks like now, compressed. And yet, it's real. Not theoretical, not some philosophical trick of language. The difference is measurable. If you had a synced atomic clock on your ship and another on Earth, by the end of your journey they disagree, not by milliseconds but by days or years, depending on how long you stay out here. Historians still argue whether this kind of one-way time travel counts as real time travel. You can't go back after all. But you can jump forward, by simply aging slower than everyone else, like a sleepy astronaut Rip Van Winkle, blinking slowly while centuries drift by outside. Back in 1971, during the Hafele-Keating experiment, scientists flew atomic clocks around the Earth in commercial planes, eastward and westward. When the clocks returned and were compared to those on the ground, the differences in time were real. Tiny, but real. That's not some high-speed spaceship. That's a Boeing 747 with bad coffee. Your ship, on the other hand, is going way faster, and you've been flying for longer, so the drift is starting to show. You pull up your ship's log. It says you've been out here for 3 weeks. The Earthside feed says you've been gone for nearly a month and a half. That's a whole week of Earth stuff you missed. 7 days of reality that passed without you. Somewhere, someone baked a birthday cake you won't eat. A politician said something weird. A band you liked had a brief comeback, then immediately broke up again. This is your life now. You're living the compressed version of the universe. A lower resolution reality, shorter days, slower time, all because you wanted to go fast. Let's take it one step further. Imagine you keep flying for years. When you finally return, you'll have lived fewer days than your friends. You'll be biologically younger, mentally fresher, still listening to the same music. Meanwhile, everyone else will have moved on, or moved up, or moved out. Some might not be there anymore. This is the tragedy of the fast traveller. The cost of speed is time itself. There's a bizarre, rarely mentioned tidbit from the early days of space travel. During the Cold War, a few science advisors joked, only sort of, that maybe the best way to preserve high-ranking decision-makers during a global catastrophe was to send them into orbit at high speed. Let them wait it out while the Earth burned below. They'd return biologically younger, and hopefully with a fresh start. Historians still argue whether this was serious policy or just very dark sarcasm, but it's rooted in truth, because time really does run differently for fast ships. Back in your pod, you think about the people watching your mission. Maybe it's a group of scientists, maybe it's one person, maybe it's just a camera in a corner of some dusty observatory, blinking transmission active. They're aging faster than you, right now. As you think this thought, they're already half a second older than when you started thinking it. It's like you're watching life on fast forward, but only for them. And in return, your life is a short story told slower, a compressed epic, a quiet whisper stretched over a very loud world. You finish your rehydrated spicy mac and realize you'll never taste this same moment again. Not because it's a unique flavor, it really isn't, but because time itself has become rare. Every second you spend moving forward in space is a second stolen from the shared rhythm of the universe. So you smile, because maybe that's the point, to drift apart from time, to live a little slower than the rest of the world, to move so fast that your life becomes one long, gentle pause. Your days might be compressed, but oh, they're yours, you're brushing your teeth. Or rather, you're brushing something vaguely mint-flavoured against your molars with a vibrating piece of tech that swears it's optimized for low-gravity oral hygiene. The paste tastes like freezer-burnt nostalgia, and your reflection in the mirror looks the same, but it shouldn't. Because you, dear space traveller, are aging like an astronaut, slowly, subtly, spectacularly out of sync with everyone else. Let's talk about how astronauts, even now, real, modern astronauts, are living proof that time dilation is more than just thought experiments and scary train metaphors. You don't have to travel at 99.99% the speed of light to age differently. You just have to leave Earth. And yes, it's already happening, right now. Let's go back to 2015, when NASA astronaut Scott Kelly spent nearly a year aboard the International Space Station. Back on Earth, his identical twin, Mark Kelly, former astronaut, current senator, and the unwitting control subject in this very weird science project, stayed home. Same DNA, same birthday. But by the time Scott returned, he was just a little bit younger than Mark. Not by much, just a fraction of a second. But still, he lived less time. Because while Scott orbited Earth at 28,000 kilometers per hour, his body, his cells, his heart, his thoughts, experienced time at a slightly slower rate than his twins. This wasn't just a curiosity. NASA actually measured it. Historians still argue whether this qualifies as true time travel. Some say it's not dramatic enough. Others say it's the only kind we'll ever get. But here's the punchline. Every single astronaut who's ever orbited Earth has come back a little younger than they would have been otherwise. They don't feel it, of course. No one disembarks the ISS looking like they've just walked through a temporal spa. But their clocks, both biological and mechanical, tell a slightly different story. And the faster and longer they travel, the bigger the difference becomes. You, however, are no ISS crew member. You're travelling much, much faster. So what does that mean for your own little space-time selfie? Well, it means you are currently in the slow lane of aging. While your friends back on Earth are racking up candles on their birthday cakes like it's a competition, you're cruising through a life that unfolds more gradually. You still age, relativity isn't immortality, but you age less per unit of Earth time. It's like having a retirement plan that kicks in early but only pays out if everyone else turns to dust first. A bizarre side effect. You might outlive everyone you know, not because you're immune to danger or somehow healthier, but because your seconds are longer than theirs. Your shipboard systems calculate that for every Earth day, you experience 20 hours, which means for a typical 10-year mission, Earth would age by 12.5 years. You'd come back younger, not by much, maybe a year or two, but in relativity, that's enough to rewrite a lifetime. You're not just skipping lines in the grocery store of time, you're living in a different store entirely. Here's a fringe fact to help you brush a little longer. In 1975, a group of Soviet physicists proposed launching a time dilation mission where a cosmonaut would orbit the Earth for decades in a highly elliptical orbit to gain measurable age differences. Their working title: Project Time Pilot. Sounds like a Netflix drama now, but they were serious. Funding and political drama eventually shut it down, but the math was solid. You spit out your toothpaste and look again at your reflection. Still no grey hairs, still the same sleepy eyes. But the truth is, you're getting away with something. You're living slower than the rest of the universe, and the only price you paid was speed. The biological processes that govern aging, cell division, protein synthesis, telomere decay, all march to the rhythm of time. And when time is stretched, so is everything that comes with it. If you had a microscope on board, and the patience, you could observe this happening in real time. Cells dividing just a tiny bit slower than their counterparts in the lab back home. Metabolic reactions taking micromoments longer. You could compare yourself to an Earth twin, again if you had one, and prove beyond a doubt that motion affects biology. And not just in some vague poetic sense. The evidence would be on your skin, in your blood, in the DNA replication logs stored in your medical bay. Because out here, you are the experiment. You think back to those early astronauts, Alan Shepard, Yuri Gagarin, Buzz Aldrin and Valentina Tereshkova. Heroes, yes, but also test cases. Their missions were short, their speeds modest. Yet even they aged just a smidge slower than their Earthbound peers. And now you, hurtling through space at 0.87 C, are living the extended remix of aging. This doesn't mean you'll live forever. Accidents happen. Nutritional paste goes bad. But it does mean that, for as long as you keep moving, your clock will run behind everyone else's. Your timeline? Yours alone. Now imagine staying in space long enough to let it accumulate. A full career. 20 years at relativistic speeds. Come home, and your siblings have grandkids. Your hometown is gone. History books now include things that happened after you left. You might return with the same thoughts, the same jokes, the same bad haircut, and find a world that has forgotten the context entirely. A quiet side effect of aging slowly. No one waits for you. But maybe that's a gift. You're no longer beholden to the timeline you were born into. You can stretch your moments longer than anyone else's. Savor them. Make peace with them. Even now, as you sip your evening tea and prepare for bed, someone on Earth is rushing to a meeting, stuck in traffic, aging faster. Their cells burning just a little more quickly. Their blood flowing in a slightly faster cadence. All while you float, immune to the rush. Out here, the pressure to hurry is gone, because hurry doesn't exist when your very seconds are longer. So you yawn, stretch your limbs in microgravity and settle in for the night. You're aging, yes, but not like the others. You're aging like an astronaut, slow, measured, elegant. There's a soft knock from the ship's alert system. A little ping just polite enough not to jar you fully awake. You blink, float free of your sleep pod, and tap the wall. A panel slides open to reveal what you already suspected, cosmic ray activity, which can only mean one thing: muons. Tiny, invisible and briefly alive, these ghostly particles streak into your story now like stubborn overachievers. They shouldn't exist long enough to reach you. They really shouldn't. And yet, they do. Tonight's topic? Dancing with muons, the little particles that cheat death by moving very, very fast. Let's set the scene. You're high above Earth now, way beyond its thick soup-like atmosphere. But if you were still planet-side, say, standing in the Alps with a particle detector, or lying in a hammock regretting your fourth coffee, you'd still be getting hit by muons, cosmic rays from space, high-energy particles born in violent events like supernovae slam into the upper layers of our atmosphere. This collision creates showers of particles, including these brief, fragile things called muons. Muons are kind of like heavier cousins of the electron, but with a major catch: they're unstable. At rest, a muon lives for just 2.2 microseconds before it decays into other particles. That's 0.00000022 seconds. Barely enough time to say hello. Now here's the weird part. That's nowhere near long enough to survive the 10 to 15 kilometers it would take to reach the Earth's surface from where they're born. They shouldn't make it. The math is brutal. Even travelling near the speed of light, they should decay long before reaching you. And yet, they do, in massive numbers. So what gives? The answer lies in time dilation. From your perspective on Earth, those muons are moving at such absurd speeds that their internal clocks are ticking slower, much slower. So even though they only get 2.2 microseconds of life in their own frame, we see them living longer, long enough to reach the ground. From the muons' perspective, it's the distance that shrinks. In their relativistic frame, Earth's surface rushes up toward them so quickly that they hit it before their brief lifespan ticks out. Two versions of the same story, two frames of reference, both true. Historians still argue whether the first detection of atmospheric muons in the 1930s was fully understood as a relativistic effect at the time. But once special relativity settled into the mainstream, muons became everyone's favourite particle to point at and say, "See? Physics works. Here's how much physics works. We've recreated the muon life extension trick in labs. We accelerate them in particle accelerators, circular racetracks for the smallest building blocks of matter, and the faster they go, the longer they live. It's repeatable, predictable, and oddly poetic. Faster equals longer life. Slower time equals more existence. If only that worked on plants." You pass by one of your ship's monitoring panels, where a detector has quietly recorded a few stray muons streaking through the hull. Nothing dangerous, they barely notice you, and you barely notice them. But each one that hits the ship is a quiet reminder that time is not what it seems. Each muon is a tiny traveller, suspended in a moment that stretches far longer than it should, solely because of speed. You too are stretching moments. Your life, your days, are lengthening, not in content but in duration relative to everything else. You and the muons, both caught in the slow waltz of relativistic aging. You head back to the main control panel and pull up a simulation. It shows a cloud chamber, those old-fashioned detectors where high-speed particles leave behind little vapour trails. You watch as a muon enters from above, draws a thin white line, and then survives. Longer than it has any right to, not because it's changed, not because it's special, but because it's fast. Here's a fun twist for your sleepy mind. If you were somehow riding on a muon, experiencing its timeline, you'd feel nothing strange. You'd be born, live your 2.2 microseconds, and decay, oblivious to the fact that, in another frame, you travelled 15 kilometers before blinking out of existence. This is the same as your ship. You're zipping through space at relativistic speeds. You don't feel slower, but everyone watching you, if anyone still is, would say you're taking your sweet time. This idea has led to all kinds of wonderfully unnecessary metaphors over the years. One quirky example? In a few speculative physics forums, muons are used to explain the idea of relative immortality. The idea being that speed, if sustained, can delay death in certain frames of reference. Of course, that's more poetic than practical. You can't outrun entropy forever, but muons get close, and so do you. You lean against the padded wall of your ship watching the data stream in. Every so often another muon gets logged. A death-cheating spark from the stars, a cosmic insect tap-dancing across your detectors before vanishing again. Somewhere, some university professor is still using this very fact, the survival of high-speed muons, as the perfect undergraduate lecture moment. It's simple, elegant, and utterly bizarre. Things live longer when they move fast, not because they're special, but because time bends to make it so. You run the numbers in your head, just to feel clever. If a muon travels at 0.998 c, its Lorentz factor is roughly 15. That means, from our perspective, it lives 15 times longer than at rest. Suddenly its 2.2 microsecond lifespan becomes over 30 microseconds. Just enough time to reach the surface. Just enough time to say, "I was here," and then gone. Particles with names you'll never remember, dancing through space and time in a way that quietly proves one of the strangest truths of the universe. Moving fast means moving differently through time. You think about that as you drift back toward your sleep pod. You wonder how many muons have danced through you already. You wonder if they know they're breaking rules, or if they're just following them better than we are. You wonder how fast you'd have to go to truly vanish into time, leaving behind only a streak of light and a slightly suspicious detector beep. Not far now, and if the muons can do it, maybe you can too. You wake to the smell of something burnt. Not catastrophically burnt, nothing's on fire, but it's the unmistakable scent of failed cooking in a pressurized metal box. You sigh. Because tonight, we're drifting into an especially absurd side of time dilation. Slow-cooked spaceships. Or what happens when your dinner, your schedule, and even your entire perception of getting things done starts falling apart at relativistic speeds. See, one of the lesser discussed tragedies of moving near the speed of light is that everything takes longer. Not for you, of course. For you, things feel normal. Time is ticking. You're aging. You're hungry. And your food packet says, microwave for 90 seconds on high. So you do. You push the button, the machine hums, the countdown begins. But somewhere, maybe in a dusty office chair at Mission Control, or a distant Earth-based monitoring station, someone is watching that same event unfold. To them, the 90 seconds on your ship stretch out. Not by much yet, but enough. The faster you go, the longer it seems to them. Your microwave timer becomes an exercise in patience. And eventually, if you go fast enough, that timer turns into a slow drama. Each beep of the keypad might take minutes. That faint humming becomes a drawn-out groan. From their perspective, your dinner is trapped in slow motion. Here's the wild part. It's not the food that's cooking slowly. It's your entire timeline. Your heartbeat, your thoughts, your very metabolism, all slowed down relative to the outside world. So yes, your dinner still cooks in 90 seconds from your point of view. But in Earth time, that same mac and cheese gets a whole lot of existential oven time. Which begs the question, what does cooking mean when time itself is playing favourites? Let's get theoretical. You're moving at, say, 0.95 C, 95% the speed of light. That's a Lorentz factor of about 3.2, meaning, from Earth's perspective, your ship's clocks are ticking roughly 3.2 times slower than theirs. So your 90-second microwave session, that's about 288 seconds, almost 5 minutes to someone back home. Now imagine doing everything on this stretched timeline. Sleeping for 8 hours becomes 25 Earth hours. A 1-hour workout, that's 3.5 hours for anyone watching from a slower frame. Even reading a book turns into a saga of glacial eye movement, at least from their view. But for you, it all feels normal. Time doesn't lag or stretch. You're not watching your hand wave through molasses. Everything's ticking along at its usual speed, your speed, which is what makes time dilation so sneaky. You don't feel it, you don't see it, but it's there, stealing your urgency, padding your days, and making every recipe you follow hopelessly incompatible with Earth's cookbook. Here's where it gets even weirder. Imagine you're trying to coordinate a video call with someone back on Earth. You both agree. We'll chat at 1800 ship time. You prep your space tea. You brush your hair into something less floaty. But when the time arrives, you connect, and nothing's happening. Because while 1800 came for you, it hasn't come for them. Not in the same way. Your clock and theirs no longer share the same tempo. And any attempt to align your schedules quickly becomes like trying to dance to two different songs at once. Historians still argue whether anyone in early relativity debates truly appreciated how annoying this would be. The equations were elegant, the implications profound. But the practicality of timing your instant ramen at 0.9 C, grossly under-discussed. You try again with dinner. This time it's Southwest-style chili with textured protein units. Very optimistic title. The microwave purrs. You float nearby, reading the label. Let's stand for 2 minutes before serving. Ah, but which minutes? Yours? Or Earth's? If someone were watching your meal prep from a stationary frame, they'd see you moving like you were underwater, the microwave light blinking in slow bursts, your fingers tapping controls in syrupy delay, the chili packet just hovering there, stewing in unhurried grace. You, however, are still just impatient. You want it done, you want to eat, and so you wait. For what feels like exactly 2 minutes. But when you finally take that first bite somewhere far away, someone's already watched the moon rise, checked their calendar, and eaten 3 normal dinners. This is the cost of motion. The faster you go, the more the universe conspires to let you cook slowly. Your engine burns fuel, your brain burns thoughts, Your stove burns calories, and all of it happens on a timer that refuses to match up with anyone else's. Want a little flavour of fringe science? There's a rare but hilarious bit of physics fanfiction in which someone tries to build the relativistic sous chef, a robotic kitchen assistant that corrects all cooking times based on your current velocity relative to your ingredients. If you're going at near light speed, the device auto-adjusts every recipe to make sure your chicken isn't technically raw in someone else's frame of reference. Historians still argue whether that was satire or someone's actual graduate thesis, but the point remains, the faster you go, the more normal becomes subjective. Your dinner is ready now. You float back to the panel, retrieve your tray, and realise that even though it says it's hot, it doesn't feel hot. Because the thermodynamics of relativistic cooking don't quite align either. See, temperature is a funny quantity in special relativity. Depending on how it's defined, and trust me, physicists have spent far too many sleepless nights arguing about this, temperature can appear to change based on the observer's frame. Some theories suggest that a fast-moving object appears colder to a stationary observer. So your chili might be warm to you, but back on Earth it looks suspiciously lukewarm. You squint at it, it squints back, you eat it anyway, and you think about how this one little meal took just a bit more time than it should have. Not because the machine was faulty, not because you made a mistake, but because your clock and the universe's clock are no longer friends. They don't even wave at each other anymore. Everything on this ship, your dinner, your to-do list, your sleep schedule, is quietly diverging from the rhythm of the cosmos. A slow drift, a widening gap. Like two songs that started in sync but gradually fall out of time. And someday, if you return to Earth, you'll find that your entire life has been slightly undercooked compared to everyone else's. But for now, you float, full, warm, quiet. And if the chili feels a little overextended, that's okay, because you're not just slow cooking food, you're slow cooking yourself. You're lying on the padded floor of your ship now, arms tucked behind your head, eyes open and unfocused, gazing up at the soft ambient glow of the cabin ceiling. It's been a quiet hour, or a few Earth hours depending on who's counting, and your mind has started to drift into deeper space. Not physically, mentally, philosophically. Because once you've wrapped your head around time dilation, and you've made peace with your slow-cooked dinner and your off-sync microwave, there's only one logical next step. Warp drives. Yep, that kind of warp drive. Tonight we tiptoe into the theoretical, dreams of the Alcubierre drive, the only idea in physics that dares to say, what if we cheat? First, let's set the stage. You already know that the speed of light, c, is the universal speed limit. Nothing with mass can reach it, nothing can exceed it. That's the whole reason time dilation happens in the first place, the universe bending over backwards to keep light's speed consistent for all observers. But what if you didn't move through space at all? What if you moved space? Enter Mexican theoretical physicist Miguel Alcubierre, who in 1994 decided to wake up one morning and absolutely ruin sci-fi purists with a single research paper. He proposed a solution to Einstein's field equations that would allow a ship to travel faster than light without breaking the laws of physics. Not by speeding up the ship, but by warping space-time around it. Here's the idea. Imagine your ship sitting inside a bubble of flat space-time. You compress space in front of the ship and expand space behind it. The ship doesn't move inside the bubble, it just rides the wave. The space itself is doing the moving. It's like surfing the universe, but instead of water, you're riding a controlled ripple of space-time distortion. The ship never travels faster than light locally, but the distance between point A and point B shrinks. A lot. If you could warp space enough, you could reach Alpha Centauri in days, not decades. Your head's already spinning, right? Good. Now let's gently untangle the mess. In standard relativity, space and time are not static. They bend in the presence of mass and energy. That's how gravity works. The moon isn't being pulled by Earth. It's following a curved path through warped space-time. Alcubierre's idea was to take this concept and weaponize it for travel. By manipulating space-time curvature in just the right way, you could create a bubble that slides faster than light relative to an outside observer. Inside the bubble, time would feel normal, no time dilation, no extreme g-forces, just you, floating in your cozy ship, sipping your tea while the universe folds around you like origami. Of course, there's a catch. There's always a catch. To create that warp bubble, Alcubierre's model requires something called negative energy density, a type of exotic matter that, as far as we know, doesn't really exist. It's the kind of stuff that would repel rather than attract, like gravity's evil twin. And not just a little bit of it. You'd need an absurd amount of this stuff, possibly more than the mass energy of the entire observable universe, just to warp a soccer ball-sized region of space. So yeah, that's a deal breaker. But not a hard no. Fringe physics is full of tweaks, addendums, and increasingly optimistic what-if papers. Some theorists suggest that quantum effects, like the Casimir effect, might produce small regions of negative energy. Others are tinkering with geometric tricks to reduce the energy cost of warp drives to something slightly less catastrophic. Historians still argue whether Alcubierre meant for his drive to be a real blueprint or just a mathematical curiosity, an experiment in what general relativity would allow, not necessarily what nature would provide. But science fiction? Oh, it pounced. Within weeks of Alcubierre's paper, writers were drafting plots. Star Trek fans were giddy, forums erupted, and even now some research groups, like NASA's speculative EagleWorks team, continue to poke at the edges of warp physics, hoping to turn an equation into an engine. Here in your ship, at 0.88 C and climbing, you can't help but imagine what it would feel like to activate a warp bubble. No more time dilation, no more relativity headaches. Just you and a jump to another star system. You reach out to the nearest console and call up a simulation. The screen shows a glowing ovoid ship encased in a rippling field, a distortion bubble sliding through the stars. The stars ahead compress into a glowing arc. The stars behind stretch into an infinite smear. No acceleration, no inertia, no stress, just motionless motion. In the sim, the ship reaches Proxima Centauri in 12 Earth days. You sip your tea. Out the window, your own stars remain fixed. No warp bubble here, no space-time origami, just honest, slow, relativistic speed. You're taking the long way. And yet, the idea lingers. Could negative energy exist? Could the laws of physics be bent just enough to allow shortcuts? Some speculate that naturally occurring warp bubbles might even exist in the distant universe, microstructures in the foam of space-time. They wouldn't be usable, but they'd be proof. Even the quantum vacuum, once thought to be a true nothingness, now buzzes with virtual particles and fluctuations. It's not empty, it's teeming. Perhaps one day, we'll learn how to tap into that chaos, to harvest it, sculpt it, use it. A fringe physicist once joked that if warp bubbles are possible, they'll probably be discovered by accident, in a lab, by someone trying to fix a leaky particle trap. Oops, we folded Toledo into a Mobius strip, you chuckle. The idea that you could simply pop from one part of the galaxy to another, skipping the slow march of time dilation, is as comforting as it is infuriating. Because for now, it's just a dream, but not an impossible one. And maybe one day you'll ride a bubble instead of a ship, maybe your descendants will, maybe someone already is. You turn off the simulation and glance at your velocity, still accelerating, still bending time behind you. And for now, that will have to be enough. You float for a while in silence. The ship makes its usual sounds, the barely there thrum of life support, the subtle whine of ionized particles slipping through the drives, the occasional ping of data arriving late from Earth. You're not surprised anymore when a message shows up timestamped yesterday, but clearly references an event from next week. Time has become slippery, greasy even, and as your ship creeps closer and closer to the edge of what's allowed, there's a question buzzing behind every sensor, every whisper of motion in this vessel. How fast can you go, really? Tonight's topic, cosmic speed limits, and why the universe built a brick wall around the speed of light, hung a sign on it that says do not enter, and then bolted it shut with physics, math, and maybe just a little cosmic pettiness. Let's say you want to go faster. You're already moving at 0.89 C now, fast enough that you've outrun every holiday back home and then some. Fast enough that Earth's clocks are starting to laugh politely as they sprint ahead of you, but you're greedy. You want 99 cents, 0.999 C, 0.999999 C. Why not? Well, because the universe isn't having it. You remember the Lorentz factor, right? That gamma symbol, gamma equals 1 divided by the square root of 1 minus v squared over c squared. As your velocity v gets closer to c, the denominator approaches 0. And what happens when you divide by 0? The math politely explodes in your face. At light speed itself, gamma becomes infinite. Your mass becomes infinite. The energy required to keep accelerating becomes infinite. And unfortunately, your ship's engine doesn't run on dreams and paradoxes. It runs on actual fuel, which runs out. You can approach light speed, sure. You can flirt with it, sneak up to it, maybe even graze its metaphorical shoulder in a crowded hallway, but you can never catch it, never match it, and definitely never pass it. Because light doesn't just move fast. Light defines fast. It's the speed limit baked into the universe's structure, woven into the equations of special relativity, embedded in the geometry of space-time, and lurking behind every particle interaction. It's not just a rule, it's reality. And the closer you get to it, the more you suffer. Your energy costs don't scale nicely. They grow exponentially. If it takes X energy to reach 0.9 C, it takes 10 times that, or more, to reach 0.99 C. By the time you get to 0.9999 C, you'd need more power than the entire Milky Way galaxy could supply. Kind of overkill just to get to the party a little sooner. But what if, hear me out, you had no mass, like a photon? Well, then you would travel at the speed of light. In fact, you'd have no choice. Photons can't go slower. They don't get to dilly-dally. Once they're born, say, from a light bulb, a star, or the atomic cascade of a muon, they launch at 299,792,458 meters per second. No warm-up, no acceleration, just immediate, uncompromising motion. And from their perspective, time doesn't pass. That's the most haunting part of the speed limit. At the speed of light, time stops entirely. A photon, born in the heart of a star and absorbed by your retina 1,000 years later, experiences that journey as a single moment. No aging, no ticking clock, no before or after. Historians still argue whether this makes light some kind of eternal observer or just the universe's ultimate introvert, moving through time without participating in it. But you still have mass, you still tick. And ticking means you obey the speed limit. Now, here's a little quirky physics trivia. In 1967, theoretical physicist Gerald Feinberg proposed the idea of tachyons, hypothetical particles that would always move faster than light, never slower. These little rebels would, by definition, exist outside the realm of causality as we know it. They could, in theory, arrive before they were sent. Send a message via tachyon. It might arrive yesterday, or 2 days ago, or before the sender was born. Needless to say, this ruffled a few feathers. Most physicists agree now that tachyons, while interesting to toy with mathematically, probably don't exist. The laws of causality, the idea that cause comes before effect, are kind of important when you're trying to not break the universe. Still, people play. You can find long-abandoned forum threads and chalkboard graffiti in grad school lounges about how to build a tachyon antenna. None of it works, but it's fun to imagine. And yet, here you are, still pressing into the upper limits of speed, still measuring your days in 2 frames, your own and Earth's, slowly peeling away behind you like an old sticker on a fast-moving car. You can feel the limitations now, not physically. Your ship is smart enough to cancel out the internal stress, but conceptually. Your acceleration brings diminishing returns. Your speed creeps higher, but the energy you're spending, it skyrockets. You push harder and get less. You watch as Earth's clock races. Yours, calm, unmoving. You feel fine, but the gap is growing, and it will never shrink again. This is the heartbreak of the cosmic speed limit. Not that you can't go faster, but that the more you try, the less the universe gives back. You pay more and more for smaller and smaller steps. Like ordering a pizza and getting only the crust each time. But maybe there's a kind of grace in that. The speed of light isn't just a wall, it's a mirror. It tells you where you stand. It draws the line between particles and waves, between presence and perception. It tells you, here is what it means to exist in time, here is the edge. Beyond this, you're something else. You float near the window watching a star shift position ever so slightly. It's not much, but it shouldn't have shifted at all. You're moving so fast now that even the orientation of your view begins to warp. The light from ahead is compressed. The light behind, red-shifted into nothing. You're entering a tunnel of your own making, a cone of forward motion where the universe collapses into a directional blur. And yet, despite all of this, you're still not at the limit. You never will be. No one will. Because light doesn't just move faster, it is the limit. It's the final boss, the last mile marker, the universal referee holding up a whistle and saying, okay, that's enough. And even as you accelerate, chasing every decimal place behind 0.99, you know this. The light in front of you will never get closer. You're not chasing a thing, you're chasing a boundary, one you'll never cross. And so you ease off the throttle. Just slightly. You're not stopping. But you understand now, the race isn't to catch the light, it's to understand what it means to never win. You're standing in the middle of your ship's galley, holding a mug that claims to be self-heating, but really just has strong opinions about being lukewarm. You're trying to decide if you want coffee, tea, or just to stare into the middle distance for a while. But the ship's internal clock just clicked over to a new local hour, and with it comes that creeping feeling again. The day doesn't feel quite right. Is it dragging, rushing, looping? Hard to tell. It's not the ship's fault. It's not even the coffee's fault, though that definitely doesn't help. No, this is deeper. This is relativity at the DMV levels of time distortion. Because tonight, we're exploring the strange sensation you already know too well. When time feels like it's stretching not because of physics, but because of you. Yes, it's time for time dilation at the DMV. And before you get smug, this isn't just a metaphor. You know the DMV, the Department of Motor Vehicles, or its local equivalent, that grey fluorescent netherworld where time crawls like molasses in winter. You take a number, you sit, you check your phone, you look up, still number 37, you look down, still number 37, you fall asleep. Somehow, it's now number 12, and they already called you 3 times. It's a place where minutes defy their proper rhythm, where seconds stretch long enough for you to evaluate every mistake you've ever made in life. It feels like time dilation, and weirdly enough, it kind of is. Now don't panic. You're not experiencing Einstein-level relativistic effects just because you've entered a boring bureaucratic building. But there's something psychologically fascinating here, something that ties directly into your interstellar journey. Time perception. It turns out our brains are terrible clocks, and I mean truly awful. We estimate time based on everything except time. Our attention, our stress levels, our emotional state, how bored we are, how much sensory input we're getting. These all mess with our internal stopwatch. When you're stimulated, say, riding a roller coaster or being chased by a bear, time seems to slow down. Your brain is processing more information, encoding more data, and it feels like each moment is longer. But in low stimulation environments, like a DMV lobby or a dimly lit spaceship with nothing scheduled for the next 7 hours, time compresses. You glance at a clock and think, how is it only 2:15? I've been alive here for centuries. You are not alone in this. Astronauts on the ISS and deep space simulation subjects in isolation report distorted senses of time all the time. Some days feel rushed, others drag endlessly. The longer the isolation, the more skewed the perception becomes. Historians still argue whether early Antarctic expeditions or long-duration submarine crews suffered more from time dysphoria. But the trend is consistent. When your environment is unchanging, your internal time begins to wobble. And on your ship moving near the speed of light, this effect gets layered over actual physical time dilation. So not only are you objectively moving through time more slowly than people on Earth, you're also subjectively experiencing time in a warped way. Because your daily routine is quiet, controlled, predictable, and your brain is begging for a change in tempo. Here's the kicker. In extreme boredom, people begin to overestimate how much time has passed. They believe more minutes have gone by than actually have, which makes time feel slow, but during exciting events, people often underestimate time, thinking it passed faster than it did. So maybe the DMV is a time machine, a slow one. With a broken seatbelt, you wander down a corridor in your ship holding your half-warm drink, thinking about how many days you've been out here. Not ship days, not Earth days, just your days. It's hard to know anymore. The logs say one thing, your body says another, and your brain, well, your brain checked out sometime after the 5th reheated space lasagna. You pass a panel and see a delayed message from Earth, a holiday greeting. It arrived 5 minutes ago, sent 3 weeks earlier. The time drift grows. You know what they're doing down there. Running errands, going to work, picking up dry cleaning, yelling at printers, and waiting at DMVS, ironically. You wonder if their time feels just as distorted as yours. Maybe not physically, but psychologically. Because here's a juicy little fringe detail. There's a growing field of research called chronoception, the study of how we perceive time, and it's full of weird ideas. Some theorists suggest our brains use dopamine as a kind of internal metronome. When we're stimulated, dopamine surges and time seems to stretch. When we're bored or stressed, dopamine drops and the beat slows down. If that's true, then your current experience isn't just physics, it's neurochemistry. You're bored at 0.9 C, a slow traveller in a fast ship, trapped between frames of reference and the mental equivalent of elevator music. This is where relativity and perception overlap like an annoying Venn diagram. Because even though your time is objectively slower, you still feel it dragging. You have more time than anyone back on Earth. But you're not sure it's worth using, so you sit, or float. You turn on a playlist and listen to a slow, dreamy synth track that somehow also feels too long. You pull up a book you've read 3 times and consider reading it backwards, just to see if the plot improves. You even consider, don't say it, organising your inbox. Time, it turns out, isn't just relative or it's rude. And just like in that dim lobby full of plastic chairs and numbered tickets, there's nothing you can do but wait it out. The ship will keep moving, your time will keep stretching, and eventually the clocks will tick over again. A new message will arrive, a new star will appear on the horizon, a new moment will begin. Until then, you sit, trapped in a paradox. The fastest ship in the universe, and nowhere to be. You're in the shower now. Well, the ship's version of a shower, which is more like being gently misted in a vacuum-sealed closet, while a polite computer voice reminds you to close your eyes before rinsing. It's efficient, not satisfying, but oddly appropriate considering tonight's theme, why you're always late now. Because yes, even here, drifting through space at nearly the speed of light, surrounded by equations instead of people, your body still clings to its one true habit, running behind schedule. But this time, it's not your fault. It's time dilations, and not the dramatic starship-level gamma factor kind. Not this time. This time we're talking about gravitational time dilation, the quiet, sneaky cousin of the more glamorous high-speed version, the one that messes with you even if you never leave Earth at all. Ready? You step out of the shower pod and float toward the mirror. You look the same, still youngish, still sleepy, still arguing with a single eyebrow hair that refuses to cooperate. But something's different. Subtle, unfelt. Your feet? They're aging slower than your head. No, really? Here's the deal. Einstein's general relativity tells us that time doesn't just warp when you move fast. It also warps when you're near mass. The stronger the gravitational field, the slower time passes. And gravity? It's not just a force pulling you down. It's the curvature of space-time itself. So when you're closer to a massive object, like say, the Earth's core, you're deeper in the gravitational well, and time ticks a little bit slower there. It's not much. On Earth, the difference between your head and your feet is measured in nanoseconds per year, but it's real, it's measurable. We've used atomic clocks placed at different altitudes to prove it. If you live in a high-rise apartment, you're technically aging faster than someone on the first floor. You'll beat them to the future by a hair's width. Historians still argue whether this is meaningful in any way other than pub trivia, but let's be honest, it makes a great dinner party fact, especially if you enjoy watching someone try to process, wait, what? Now scale it up. Imagine you're orbiting Earth in the International Space Station. You're farther from Earth's centre, so gravity's weaker, meaning time moves a bit faster, but you're also moving at 28,000 kilometers per hour, which means time slows down due to special relativity. So you've got competing effects, speed and gravity, pulling time in opposite directions. The net result? Time actually moves slightly slower on the ISS, but it's close. This duality is everywhere. You walk up a flight of stairs? Congratulations, you've just aged fractionally faster than someone downstairs. You climb a mountain? Even more. That long hike wasn't just cardio, it was time travel. Now your spaceship, it's gliding far from any massive object. Out here, in deep space, gravity's whisper is barely audible. That means time should be ticking faster than it would on Earth, but you're also moving fast. So once again, you've got the push and pull, less gravity, faster time, but more speed, slower time. Which one wins? In your case, velocity wins by a landslide. You're aging slower, relative to Earth, because your speed overwhelms the gravitational boost. But back home, that tension exists all the time. Your grandma living at sea level, she's technically younger than your uncle in Denver. Your cat who sleeps on the top shelf of the closet, slightly older than the one napping under the couch. Time is picky, petty, pet-specific. You pass by the ship's main console and glance at the synced clocks again. One shows shipboard time, the other, Earth time. The difference now is over a week. You've lived fewer days than everyone back home, a full 7 days less, and you still haven't finished that book. You tap a few keys and pull up a simulation, one of your favourites. It's a 3D model of Earth, colour-coded by time dilation. Reds for slower time, blues for faster. Mountain peaks glow faintly. Deep mines flicker with red light. Satellites shimmer in shifting shades as they orbit in complicated loops of speed and altitude. Everywhere you look, time is out of sync with itself. We just pretend it isn't. You float, arms crossed, staring at the glowing model, and ask the question you always ask. Why do we still pretend time is absolute? Is it because clocks are round? Because calendars are tidy? Because it's easier to say meet me at 3 than to clarify which 3 o'clock, whose reference frame, how much gravity and how fast they're moving? Or is it because admitting time is fluid makes us feel untethered? That if time isn't fixed, then maybe nothing is? Here's a fringe nugget to chew on. Some ancient civilizations believed time flowed differently for gods and mortals. A year for the gods could be a day for us. They weren't thinking about Lorentz transformations, but they were, somehow, on the right path. Maybe they sensed what we've now proven, that time is a local phenomenon, a personal one. You close the simulation. The stars outside are still fixed in place. No new messages, just silence and the quiet tick of your own time stretching away from everything else. And you realize something both sad and strangely funny. You're not late. Everyone else is just running early. Your ship's course is plotted now with eerie precision, and yet the stars ahead look wrong. It's not that they've shifted out of place. It's more that you have. Maybe it's the velocity, maybe it's the isolation, or maybe it's the story your onboard systems are showing you now. A simulation you've watched exactly once and quietly promised yourself you'd never revisit. But tonight, you do. You tap the screen. The blackness comes alive, and you fall into one of the darkest truths in physics. Tonight you spiral toward black holes and the timeless scream. Here's how it begins. You're drifting peacefully through deep space when a massive object starts to influence your course. Not visibly, at first. Your ship doesn't lurch. There's no alien soundtrack, just a subtle increase in gravitational pull, and then, on your screen, a label appears. Sagittarius, a star. Supermassive black hole. 4 million solar masses. Center of the Milky Way. You're not near it, not yet. But the simulation lets you go there anyway, because you want to know. What does it mean, truly, when physicists say that black holes bend time? Let's start small. Black holes aren't just things, they're boundaries. A black hole is defined by its event horizon, a region where escape velocity exceeds the speed of light. Not even photons can claw their way out, which of course brings us right back to relativity. If light can't escape, and light sets the speed limit for everything in the universe, then anything that crosses that event horizon is cut off from the rest of space-time. From the outside, an object falling into a black hole appears to slow down. The closer it gets, the slower it moves, until, at the very edge, it seems frozen, hovering, eternally paused. We call this gravitational time dilation, on steroids. Remember the clock on a mountain thing? Same principle, just cranked up so high it starts to shatter meaning. Because here's the twist. From the falling object's perspective, time feels normal. You accelerate, you pass the event horizon, you reach the center, you get torn apart, maybe not in that order, but to the observer outside, you never fall, you never land, you never finish, you just stop. Light from your ship becomes red-shifted, its wavelength stretched longer and longer until it fades from view entirely. Your scream, if you tried one, would deepen, slow, and stretch into silence. A timeless scream, forever lingering at the edge of a place no one can ever return from. Historians still argue whether time inside a black hole is meaningful at all. Some say the singularity, the point at the center where density becomes infinite, is the end of time itself. Others say time continues, but in ways our equations can no longer describe. Back in 2014, the movie Interstellar popularized the idea of time dilation near black holes. You remember it, right? A planet orbiting a massive black hole, where a single hour equals 7 years elsewhere. That wasn't just Hollywood fantasy. The math checks out. A strong enough gravitational field really can slow time that drastically. In the simulation, you follow a tiny probe as it descends toward the event horizon. On your ship's clock, the journey takes minutes, but your external observer's clock stretches it out. Hours, years, eventually centuries, and still the probe never crosses the line, not from their view. It's the ultimate paradox. You reach the point of no return, but from everyone else's frame, you never arrive. You're suspended, eternal, a frozen moment spiraling in. This isn't just theoretical. We've observed stars near the supermassive black hole at the center of our galaxy. Their light shifts, their orbits bend. They agree with Einstein. Time is slowing for them, not enough to notice casually, but enough to measure. And if a star can feel that slow down, what would a conscious being feel? Some researchers think, theoretically, that if you could somehow survive the tidal forces, those bone-snapping gravitational gradients, you might experience a few seconds of time from your own perspective, even as billions of years pass outside. Fall into the right kind of black hole and you might outlive the universe. But you wouldn't know it. You'd be trapped in a private timeline. The rest of space would accelerate into entropy, galaxies fading, stars dying, atoms cooling, while you drift into your last breath. A lonely miracle. You think of that as you stare out the window. Your ship isn't heading toward a black hole, but your velocity is high enough now that time dilation is starting to resemble gravitational effects. In both cases, what matters is the warping of space-time, one caused by mass, the other by motion. The math rhymes. So you think, is my ship becoming a kind of artificial black hole? Not in the literal sense. You're not crushing stars in your glove compartment. But in terms of time, maybe. From Earth's perspective, you're crawling. From your perspective, they're sprinting. And in some distant future, someone might look at the data logs and see your signal still streaming in, your clock still ticking, long after they expected you to be gone. From their perspective, you're still here. From your perspective, you've already moved on. Here's a fringe theory to chew on as you float. Some researchers propose that information falling into a black hole isn't lost, but encoded on its surface, the event horizon, like a cosmic hologram, meaning your ship, your journey, your thoughts, your scream, could all be preserved in some form on the very edge of time. What a legacy. To be a shadow on the skin of a singularity. A whisper no one can hear, but that never truly vanishes. You pull back from the simulation. The stars outside have not changed, but something inside you has. You understand now why the universe is so stingy with speed, why the closer you get to light, the more time slips away. Because to go faster is to go deeper into time's distortion, to vanish into stretched seconds and frozen frames, to become part of a story that no one can finish reading. You look at your reflection in the glass, still here, still ticking, but slower than the rest of the cosmos. You're a moment spiraling inward, not toward a black hole, but toward the edge of meaning itself. There's a moment, quiet, suspended, almost fragile, where you find yourself just drifting. Not in space, though that's technically true. Not in thought, though you've definitely slipped into those folds. This is different. It feels like you've lost your coordinates, not physically, but cosmologically. And so tonight, you take the scenic route through an invisible landscape. Welcome to Hitchhiking Through Minkowski Space, where space-time isn't a backdrop, it's the vehicle. Your ship hums along, your course plotted as usual. But if you could zoom out, not just from your ship, but from three-dimensional space altogether, you'd see something stranger than star charts. You'd see world lines. Picture this. Every object in the universe, from atoms to astronauts, traces a path through four-dimensional space-time. That path is called a world line. It's not where you are, it's where and when you've been. A timeline that coils behind you like a glowing ribbon. In this geometry, movement through space means a tilt in your world line. Movement through time means staying vertical. And when you move at light speed, your world line becomes a 45-degree line, slanted perfectly across the space-time graph, like a photon's clean little signature. All of this comes from a mathematician named Hermann Minkowski, who in 1908, just 3 years after Einstein published special relativity, took the whole idea and gave it geometry. He didn't just say time and space were linked, he graphed it. Space by itself and time by itself, he said, are doomed to fade away into mere shadows. Only a kind of union of the two will preserve an independent reality. Boom. With that, he turned the entire universe into a graphing exercise. Historians still argue whether Minkowski fully realized just how visually powerful his idea was, but physicists latched onto it fast. Space-time diagrams became the new compass. No longer did we talk about motion in space and time separately. Instead, we talked about where you are in the fabric. And here's the trip. You're always moving through space-time, even when you're at rest. Think about that. You, lying motionless in your ship, staring at the stars, you're still moving. Not through space, but through time. Your world line isn't flat, it's vertical. You're travelling along it at 1 second per second. It's your default speed through time. But when you start moving through space, when you accelerate, something curious happens. You steal speed from your time travel. The faster you go in space, the slower you go in time. This is the heart of time dilation. You're not just moving through space and also time. You're balancing motion within space-time. Your total motion budget is fixed. You're always moving at the speed of light, not through space, but through space-time as a whole. When you're stationary, all of that motion goes into travelling through time. When you're moving fast, some of that gets redirected into spatial movement, and your time travel slows down accordingly. Let that settle. No matter what you do, your path through space-time always totals out to the same magnitude. You're a vector. You're a line on a graph. You're hitchhiking along a 4-dimensional curve. You think back to Earth. Think about standing still, say, on a sidewalk. Your world line is vertical. You're not going anywhere in space, so all your movement is temporal. Now imagine a passing cyclist. Their world line is tilted because they're moving through both space and time. Now picture your ship. Your world line is bent at a steep angle. You're blazing through space, which means your time component, your forward movement along the t-axis, is compressed. That's why you age slower. That's why your clock ticks behind Earth's. That's why you feel suspended in a cocoon of long seconds while the universe rushes past you. And in the great graph paper universe Minkowski drew for us, this all makes sense. It's just geometry, curves and slopes and tilted lines through invisible terrain. Of course, you're not literally drawing lines behind your ship. But if someone out there, some 4-dimensional being, were watching, they'd see your path through space-time glowing like a neon thread. Maybe that's what the universe looks like to whatever's watching us from the outside. Just tangled lines, brushing, intersecting, splitting off. Like constellations that record not stars but lives. You pause at a console and call up a real-time space-time diagram. Your world line arcs slightly, showing your acceleration. You're not moving in a straight line anymore. There's curvature now. Subtle bends that show your journey isn't just fast, it's changing. You're carving a path, not just travelling it. Here's a fringe detail for the late-night thinkers. Some physicists have suggested that world lines may interact with quantum effects, that in certain quantum interpretations, a particle's entire world line must be accounted for, not just where it is now, but where it's been and where it might go. That past, present and future aren't just points, they're all wrapped into the line. So when you say I am here in space-time terms, you're really saying I am this line, extending across the 4th dimension. You are not a dot, you're a shape, and you're still drawing. Back on Earth, most people never think about this. They walk, run, sleep, without ever realizing that they're slowly tracing their stories into a fabric that doesn't forget. But you're watching it in real time. Your ship moves, your time warps, your line stretches at angles no human has experienced before, and you begin to see the beauty in it. Space-time isn't something you pass through, it's something you write into. Every second you live is another point on the page, every motion a new direction in your script, and even if no one reads it, even if your world line drifts in silence forever, it's still there, in the shape of your journey, in the slope of your seconds, in the whisper of time as geometry. You close the simulation, you step away from the console, and you smile, just a little, because now you understand something that took Einstein, Minkowski, and an entire century of physics to uncover. You're not just travelling through space, you're carving your signature into space-time itself. You're curled up near the main viewing window again, legs tucked in, mug floating just far enough from your hand to be annoying. You reach for it, catch it on the 3rd try, and take a sip of something warm and vaguely vanilla adjacent. Outside, the stars remain patient, but you're no longer asking where you are, you're wondering when. Because tonight you get brave. You ask the question most people are too polite to bring up in physics class. What even is a second? It's such a small thing. A second, a tick, a beep, a pause between moments. But here you are, living your life, what's left of it anyway, 1 second at a time, even as those seconds stretch and warp and cheat depending on how fast you go. So what is a second, really? Let's dig in. The original definition of a second was tied to the Earth's rotation. People chopped up the day into 24 hours, each hour into 60 minutes, each minute into, you guessed it, 60 seconds. That made one day 86,400 seconds long. Nice, neat, ancient, but not perfect. Because Earth, as it turns out, is a little wobbly. Its rotation isn't perfectly consistent. It speeds up, slows down, gets nudged by the moon, earthquakes, solar activity, political unrest. Okay, maybe not that last one. And when you're talking about relativity and GPS satellites and people aging at different rates, precision matters. So in 1967, physicists decided to toss the spinning rock idea and define a second in terms of something much more stable, atomic transitions. Specifically the cesium-133 atom. This little nugget of quantum reliability vibrates in a very specific way when its electrons jump between energy levels. In fact, it oscillates 9,192,631,770 times per second. So now, that number of oscillations equals 1 official SE second. Boom, defined. So every tick of your clock isn't some arbitrary flick of a hand. It's the universe dancing to cesium's rhythm. A vibration, a count, a certainty. You take a breath. But now you're wondering, does that still hold true when you're moving at near light speed? Do cesium atoms on your ship still oscillate 9,192,631,770 times per second? Answer, yes. But it gets weird. Because from your perspective, your cesium clock is doing just fine. Still ticking, still accurate, still giving you proper Earth-certified seconds. But to an observer outside your fast-moving frame, your entire atomic clock is slower. The oscillations are stretched, the seconds become longer. Time dilation doesn't care about your official definitions. It stretches your entire experience, including how many atomic jiggles fit into a second. Here's a bizarre thought experiment for you. Imagine 2 cesium clocks, identical in every way, except one is moving at high speed. You synchronize them, then you check them after a while. The moving one reads less time, fewer oscillations, fewer seconds. The clocks disagree, not because they're faulty, but because time itself is playing favourites. It's not just perception, it's measurable. This isn't hypothetical, it's been done. In 2010, researchers at the National Institute of Standards and Technology put 2 atomic clocks on different shelves, just 33 centimetres apart in height. The higher clock, farther from Earth's gravity, ticked slightly faster, by mere billionths of a second. But those billionths, they count. Historians still argue whether this experiment really changed our understanding of time, or just confirmed what Einstein had already ruined for everyone. Either way, it proved the point. A second isn't universal. It's local, it's conditional. It depends where you are, how fast you're going, and how deep you are in a gravity well. So now the second, the very thing that defines all other measurements of time, is itself flexible. You sit back and think about how many seconds you've burned on this journey, how many stretched and contorted cesium oscillations have passed since launch. Your shipboard clocks say one thing, Earth says another, and the worst part? They're both right, because time doesn't flow the same for everyone. It doesn't even agree with itself. Which leads to a truly spicy idea whispered in late-night labs and sci-fi fan forums alike. Time is an illusion, more specifically a coordinate, a label, a position in a 4-dimensional structure we happen to be sliding through in one direction because of entropy and memory and biology. Some physicists have even proposed that the flow of time is an emergent property, something that comes from the way particles interact, not a fundamental feature of the universe. Like how temperature is real, but only in the statistical behavior of molecules. Time might be the same, not a river, just a pattern. Cue the existential dread. You stretch your fingers and consider what it means to live inside a measurement system that lies to you gently with every tick. Because it feels so real. The beat of your heart, the length of a breath, the pause between thoughts. You live in seconds. Even out here, racing near light speed, you cling to them like oxygen. But those seconds are stretched, bent, massaged by relativity into something personal. Here's one more quirky twist to send you into sleep mode. There are other kinds of seconds too. In astronomy, in ancient navigation, in the rhythms of the human body. Some marine animals, like certain whales, can experience time more slowly, not in the relativistic sense, but perceptually. Their neurons fire slower. Their lives unfold at a tempo we can't quite follow. To them, a second may feel longer. So even in biology, the idea of 1 second is more of a consensus than a constant. You float back toward your bunk, thinking about the 9 billion cesium jiggles that have been defining your life this whole time. You trust them, you need them. But you also know now, they aren't sacred. They're situational, they're conditional. And as you fall asleep, the last thought drifting through your head is this. The second, the most trusted building block of your time, is just a local suggestion. Out here, where speed bends space and gravity mutters secrets, even your definition of a moment can't be trusted. But that's okay, because in this ship, in this story, your seconds are yours. No matter how weird they get, you wake with a shiver, not from cold, not even from fear, but from that peculiar ripple your mind makes when it steps somewhere it wasn't supposed to go. A place outside the ordinary flow of cause and effect, a place where timelines fray and fold, where logic eats its own tail. You sit up slowly, sip from a pouch of something warm, then you ask the question out loud just to hear how ridiculous it sounds in zero gravity. What if you went fast enough to meet your grandfather? Tonight we're unraveling the delicious chaos of the speedy grandfather paradox and debating causality with your future self, who, just to complicate things, might actually be younger than you. Let's start at the heart of it. The grandfather paradox is the classic time travel problem. The thought experiment goes like this. Suppose you travel back in time and prevent your grandfather from meeting your grandmother. If you do that, you'll never be born. But if you're never born, who went back to stop them from meeting? It's a loop, a contradiction, a cosmic glitch that eats itself like a Mobius bagel. Now normally this is just science fiction daydreaming. Back to the Future, Doctor Who, Time Cop, the usual suspects. But when you start seriously studying time dilation, and especially the possibility of faster-than-light travel or closed time-like curves, oh yes, that's a real term, you brush shoulders with this paradox again. Because the closer you get to the speed of light, the more slippery causality becomes. Let's say you travel far away from Earth at near light speed, then turn around and return. Due to time dilation, you've aged less than everyone on Earth. We've already seen this in the twin paradox. Your twin is older, wiser, maybe finally gave away your vintage record collection. But now add one layer of theoretical spice. What if, using some speculative physics, maybe a wormhole, or a warp drive, or just a very persuasive plot device, you could return before you left? Congratulations, you've just created the conditions for a causality violation. Here's how that plays out in the most awkward way possible. You land your ship, step out and run into yourself, your past self, about to board the ship. Only now you know what's going to happen. You've lived the journey, you've seen the results, and maybe you decide to stop yourself from leaving, or maybe your future self tries to stop you. Now you're both shouting across the launch bay, arguing over decisions that haven't happened yet. Maybe you start throwing snacks. Maybe it escalates into a full philosophical meltdown. But no matter how you slice it, you've created a paradox. Because if you successfully prevent your own departure, then the version of you who returned never made the trip. But if you didn't make the trip, how did you return? It's a logical knot, and physicists love it. Historians still argue whether these kinds of time paradoxes are actual barriers to faster-than-light travel, or just warnings about how little we understand about temporal mechanics. Some say paradoxes prove such travel is impossible. Others argue they merely suggest our assumptions about time are incomplete. Now enter the fringe. In the 1980s, physicist Kip Thorne and colleagues showed that closed time-like curves, paths through space-time that loop back on themselves, might be possible under certain conditions, like those found near traversable wormholes. In theory, you could send a message or a person back to an earlier point in time without violating the equations of general relativity. And then things get messy. Because causality, the idea that every effect has a cause, depends on time moving forward. It depends on no message arriving before it's sent, no action happening before the decision. But in a looped space-time, you might find yourself caught in a narrative where the effect causes the cause. You receive a letter warning you not to take a flight. You follow the warning and stay home. The next day the flight crashes. You write a warning letter, you send it back in time, and now the loop exists, even though no one ever made the original decision to write the letter. This is called a self-consistent timeline, a causal loop with no beginning. It sounds fictional, absurd, but math says it's possible. Just not testable, not yet. Your ship, fast as it is, still obeys special relativity. You haven't broken causality. You haven't looped. You haven't met your grandfather, or prevented your own launch, or caused your own birth certificate to spontaneously vanish. But the closer you get to light speed, the more you tangle with time, the more you start to feel it fraying at the edges. A delayed message arrives from Earth. It references something you haven't done yet. You check the timestamp. It's accurate. You check the logs. It shouldn't be possible. But here it is. You reread it. A suggestion, a warning, or maybe just a joke from someone who knows you'll understand it later. Either way, it leaves you unsettled. Time dilation doesn't break causality, but it does make you aware of how fragile our sense of before and after really is. When clocks move at different rates, when simultaneity dissolves, when every second is relative, what happens to first? What happens to next? You float toward the rear observation deck and look back. Somewhere far behind, Earth is spinning along its own timeline, millions of people all moving forward, all assuming that events unfold in a straight line. But your line is curved now, tilted, bent by velocity, warped by distance. You've become untethered from the absolute. You are your own timestamp, and just for a moment you imagine stepping out of your ship and meeting yourself on the landing pad. Older, younger, impossible. You imagine the conversation, the contradictions, the apology for ever buying that haircut in 2031. Then you shake your head. Not yet. For now, the paradox remains a thought experiment. You still live on one side of the equation. But the equations themselves? They are watching. You wake to silence. Not just the usual shipboard hush, the faint hum of the engines, the occasional pulse of power through the walls, but actual silence. No new messages, no notifications, no blips on the long-range scanner, just an empty dashboard and a soft glow bathing the cabin in static twilight. You sit up slowly, the silence sticking to your skin like velvet. You check the chronometer, and then you check it again, because the numbers are wrong, or rather they're over. Welcome to your final destination. You made it to the end of time. The ship's systems report you've been in motion for what to you feels like a few months, maybe a year. But your Earth-linked relay, despite its lag, is now returning timestamps that read something impossible. The year is 13,870,284,012. The stars are still there, but different, fewer, farther apart, colder, older. You've outlived humanity, or at least outlived what you knew of it. How? You scroll back through the logs. Somewhere along the way, your ship passed the 0.999999999C threshold. You crossed from slow time to suspended time. Every tick of your clock became a decade, then a century, then 1,000 years. You didn't notice because inside the ship, inside your bubble of velocity, everything stayed the same. Your heart beat normally, you sipped your tea, you listened to the same 10 lo-fi playlists on shuffle. But outside, the cosmos ran out the clock. This is the extreme end of time dilation, the logical conclusion of chasing the speed of light for long enough. From your perspective, you simply accelerated, but from the universe's perspective, you vanished into the future. Now it's here, and there's no one left to see it. Outside the ship, the universe has stretched. Galaxies have drifted apart. Stars have burned out. The sky looks quieter, dimmer. You run a scan of your surroundings, and most of the results come back blank. Empty fields of radiation, isolated neutron stars, the stretched corpses of old light. No signals, no transmissions, no signs of life. You haven't just gone fast, you've outrun history. It's a lonely triumph, and yet strangely comforting. Because here, at the edge of entropy, the laws of physics still work. Your ship still hums, your heartbeat still ticks. Time is still happening, for you. Historians no longer exist to argue about this, but if they did, they'd be arguing whether you've travelled through time or merely ignored it. But that's the beauty of relativity. It doesn't care how poetic your definitions are. It just stretches time until meaning breaks. And here you are, the final time traveller. You run a few quiet diagnostics. Your onboard cesium clock still counts its 9,192,000,000. 631,770 wiggles per second. Your systems still ping the occasional rogue muon from the vacuum. You even managed to find a single ancient galaxy, still shedding light from when the universe was younger than a goldfish. But everything else? Gone. No more Earth. No more sun. No more back home. You imagine what might have happened in your absence. Civilizations rising, falling, the oceans boiling, AI waking up, AI giving up. Perhaps someone else tried what you did and flew faster, but not far enough. Only you made it here. The end of time is quiet, not a bang, not even a whisper, just a long, slow fade. Here's a fringe idea that's haunted physicists for decades. The universe might not end with a crunch or a pop, but with a heat death, a state of maximum entropy where no more work can be done, no energy gradients exist, no complexity remains. Everything becomes uniform, cold, still. You may have arrived at the doorstep of that end, a speck of warmth in the dying chill, a relic of velocity. You float to the observation deck one last time. You stare out at the void, not dark, not light, just empty. The background radiation, the echo of the Big Bang itself, has cooled into oblivion. There's no direction anymore, no up, no down, just vectors of past motion and the stubborn rhythm of your own existence. You, moving, still. A whisper of time stretched so thin it can no longer echo. And here's the final twist, the one the equations have always hinted at but never promised. If you truly reach the limit of time dilation, if you could coast at the perfect edge of light speed, your time would freeze. You'd become timeless, not immortal, just paused. You could cross the entire life of the universe in an instant. You'd never notice. You'd be a traveller whose journey was the destination. You take a breath. It might be the last breath the universe hears. You smile, not because you understand everything, but because you understand enough. You chased light, and time chased you, and somewhere in that chase you slipped the leash. No more clocks, no more calendars, just one final, eternal moment, yours forever. So now, in this quiet ship drifting through stretched time and faded starlight, you settle your weight. Not into a chair, not even into a bunk, but into the calm knowing that your journey has finished. Not with a bang, not with some grand revelation, but with something slower, something stiller. Time is no longer chasing you. It's curled up beside you like a tired dog. And though it once stretched and shrank, sped and stalled, now it just sighs, a single, eternal breath, easing its way through the last motion of the universe. You stretch your fingers, your thoughts drifting like cosmic dust. There are no more clocks to check, no more coordinates to plot. You have outlived the noise, outpaced the ticking. You've coasted quietly to the edge of meaning, and now you rest. Let the stillness hum around you like a lullaby written in background radiation. Let the stars, faint as they are, keep watch as your breath slows, your mind softens, and your eyelids begin to float downward. Nothing left to do, nowhere left to be. Just this gentle, endless moment, yours and yours alone. Sleep deeply, traveller, the universe will wait.